Now that we have our dot product and our cross product down, we're going to learn now how to use these vector and scalar products to write equations for lines, line segments, and then also planes in space. We're going to start focusing on just the lines and the line segments. One thing we want to keep in mind is that these representations are going to carry through for the remainder of the text. So if we begin focusing on lines and line segments in space, in order for us to write the equation of a line, if we think about it algebraically, we needed a point and a slope. Now the slope gives us direction. So in this case, we're going to say we need a point and a direction, or rather a position. So looking at what we have here, we have a line in space which is parallel to this vector v. So L, we're calling that the line in space. It originates at some point P naught with x naught, y naught, z naught as its components, and then it terminates at point P, x, y, and z. So the direction is going to be determined by this parallel vector v. So we have a point and a direction, or in algebraic terms, thinking about algebra, we have a slope, right? So thinking about how this v vector is formed, we have one vector that takes us to P naught and one vector that takes us to P, P being some point we chose on the line. We can find this A vector here, which is exactly the same as what we want to talk about when we talk about V. Of course, it's always helpful for us if our vectors originate at the origin, so it might be helpful to think about that V. V is just a parallel vector. It's equal in magnitude to A, the difference between P naught and P. And being a parallel vector in space, it's in space, we can start it or originate it here at the origin to help us. So I'm going to take this A part out, and then, you can kind of see that parallelogram that we use a lot when we're dealing with vectors forming in here. So as we said, the equation of this line, we need a point and a position. The point is going to be determined by P naught, and the position is going to be determined by that vector V. So what we can say here is the vector from P naught to P, or that vector A I had drawn in there a second ago, right? This vector. This is going to be equal to some T times a vector V. Vector V being this direction, and T just being a scalar multiple. So with that said, we can take this vector equation for a line in space and rewrite it as the following. Here we can see we've got our equation for the vector equation of a line L through some initial point P naught, which is parallel to V. So the vector R in terms of T equals R naught, a vector, plus some scalar T times the vector V, which T times V is just the length of that vector from P naught to P. So my R naught vector is this guy going from the origin to my initial point on that line. So R naught is this guy right here. So restating it, the R vector, R of T, that is the position vector at point P, and R naught is the position vector going from the origin to P naught. So R of T being that position vector, that's going to take us from the origin to the terminal point. So evaluating this for different values of T, different scalar values of that unit vector, that's going to give us different points on the line. And of course, we say here that T needs to be evaluated as a real number. T is between negative infinity and positive infinity. So we have infinite points on a line. There are infinite choices for t to help us develop the equation of that line. And just considering these t values, if you plug in positive t values, they're going to go to the right of the initial point. Plugging in negative t values would go to the left of that initial point. So there are multiple ways that we can express vectors. Another way we might see this is my r of t vector, which would have been written in component form x, y, z. My r vector written in component form, so that's my r naught vector, I should say. We've got x naught, y naught, and z naught. And my v vector, I have v sub 1, v sub 2, and v sub 3. So I can rewrite this. I can say, well, that x, y, z vector is equal to my x component here. We've got x sub 0 plus some scalar multiple t of v sub 1, y naught plus some scalar multiple t of v sub 2, and z naught plus t, the scalar multiple, times v sub 3. So you see we have our three components here of our original vector, x, y, z, that we wanted to determine. And this leads us to the parametric equations for a line. So the parametric equations for a line can be determined by using this standard parametrization. So if we have an initial point, we have an initial point p naught or p sub 0 and our v vector. What we can say then is that x equals x sub 0 plus t v sub 1, y equals y sub 0 plus t v sub 2, and z equals z sub 0 plus t, that would be v sub 3. And of course, this holds for any t value as long as it is a real number. So on the next slide, we're going to find a parametric equation, or the parametric equations, for a line passing through 2 points. So here we're going to find the parametric equations for the lines which pass through these 2 points, P and Q. And of course, in order for us to do this, we need to know what that vector PQ is. So the vector PQ is going to be 1 minus negative 3, which is 4i, negative 1 minus 2, negative 3j, and 4 minus negative 3 plus 7k. This vector PQ is parallel to the line and the parametric equations. So with our initial point, x sub 0, y sub 0, z sub 0, the initial point, we'll call that our p naught, or in this case, it's just p, negative 3, 2, and negative 3. With that given, we can determine that x is negative 3 plus 4 of the t. So x is, I'll use that color, we'll say, x is negative 3 plus 4t. Y would be 2 minus 3t. And my z would be negative 3 plus 7t. And so this is my solution. These represent the parametric equations for the line through that point. Now, for my x naught, y naught, and z naught, I chose point P, but it's also possible to choose point Q. So what we notice here is that the parametrizations are not unique per se, because both the base point and the parameter can change. So if I had chosen this point here to be my Q value, 1, -1, and 4, then X would be 1 plus 4t, Y would be -1 minus 3t, and Z would be 4 plus 7t. This second set of equations I've found here, they serve as well as the first. They simply place you at different points on the line for a different value of t. So we're not going to use that for the next example. We're going to build on this example and on these parametrizations. And the next thing we're going to do is we're going to parametrize the line segment which joins those 2 points. So as I said, we're going to parametrize the line segment joining those same 2 points, P and Q. I'm going to pull some of the information that we found on the previous slide onto this slide. So we're going to begin with the parametrization from the previous example. So that allows me to identify a point, X, Y, Z, and I'll call that -3 plus 4t for my X, 2 minus 3t for my Y, and -3 plus 7t for my Z. So this point passes through point P, passes through this point when t equals 0, and then through point Q at t equals 1. So what this allows us to do, it allows us to add the parameter, right? My parameter here, we're going to say that t is some value between 0 and 1, or rather, t is between 0 and 1. So this makes sense to consider a line from P through or to Q as the path of this particle is moving from our initial P naught or P sub 0 point, which in this case is P at t equals 0, in the direction of the vector V towards Q. So Q being our terminal point. So I'm going to pull in a picture to kind of help us think about what we were looking at. So here are our vectors in 3 space, and this, we derived a parametrization of this line segment from point P at t equals 0 to point Q at t equals 1. And the arrow shows the direction over an increasing time interval, or t interval, right? So we go from t equals 0 to t equals 1, and that goes from point P to point Q.